day 31, LeetCode, everyday LeetCode, right? So it's July 15, daily LeetCode, day 31. Reflections on yesterday. Yesterday was 30 days. I wish it was 30 months of LeetCode, but it wasn't. We fried reverse list, right? We got fried by longest palindrome, right? And then afterwards, I'm missing a problem here. Was it O1 matrix? Let me double check. I mean, actually, I think it's fine. But we tried longest palindrome yesterday. We got fried by it, right? And O1 matrix didn't exactly go that well either. So I'm thinking today we'll probably do both of these problems in some aspect, but we'll probably start with update matrix since that was what I was stuck on. I'm realizing now, now I understand exactly why I didn't understand the problem. Originally, I couldn't really understand why I wasn't getting the right answer. And I don't think I didn't know how to get the right answer. I just didn't really understand the premise of the problem. I think I do get it now. So we should be able to solve it. That being said, I want to shout out a comment that I got on the last video from Yeah, It's Me. And I mean, it's him. What else can you say about him? He's the guy, right? And he said, keep going, man. Nothing stops a man grinding for its future. Facts. Facts, indeed. So, it's always nice to see stuff like that. It's pretty cool. Pretty cool. Appreciate the support. And I'm trying to support him as well because he's the guy. I mean, I'm really just a student. So, that's pretty cool. That being said, make sure to join the Hyperbolic Coding Chamber Discord. Thousands upon thousands of people joining every day. At the same time, we have some problems to do. And actually kind of short on time today. So I'm just going to jump into it. And we got 1 hour and 30 minutes, 20 minutes. Goals for the session would be to be able to do O1 matrix and longest palindrome. And then still touch maybe K closest points to origin. I've never even done a heap problem before. So that would be ideal. And then from here, we can actually start making some progress on some mediums. Right. So that would be ideal. So I would say let's jump into it, right? So put an hour. So we have O1 matrix. So let's do that, right? We have 20 minutes, probably good to see our time. And I'm going to do one more thing. So here we are deep, right? So we have O1 matrix given an M by N binary matrix mat, right? Return the distance of the nearest zero for each cell, right? Of the nearest zero. And so I think what I didn't understand last time, it's just the nearest distance, the nearest zero to the cell. So it's really just in general, what is the nearest distance, right? And what I was doing before, I was trying to basically only travel in a certain direction when they're asking for the nearest distance in general, right? And the way we get that distance is just by doing the absolute value of the positions themselves. So if we wanted to get the distance between this 0 and this 1, we wouldn't count the steps we took to get there. Oh, I mean, you can't travel diagonally. You can only travel up, left, right, or down, but it technically takes the distance between them would be the output here, right, would be 2 because the closest 0 is 2 moves away. And so it's up, right. So you actually can't travel directionally. And that was really my problem in the end. And so I'm thinking now, right, we could do this with a depth first search and just check if we start the depth first search when we reach 1, right, maybe what we could do is we could travel up, down, left, right, and for each of these nodes, we'll also travel up, down, left, right. and see if we can find a 0. If we find a 0, we'll return it, and then we'll basically take the math.min of all of those 4. Now originally my older version traveled only going one direction, right? This version will not do that. It'll be much more natural, I guess. And so let's just say if we start at 1, right, we ask it to do a depth first search, we'd go up, we'd see a 0, right? And so the closest 0 would be 1 spot away. And if we go right from there, right, once we find a 0, we just want to return it, right? So I guess the problem would be in a case where we have something like 1. If we have 1, right, if we started depth first search, right, we'd go up, right? We're not at a 0 yet, right? So then we would go up, and then we'd have a 0. So we can just return. So I think the first 0 we find, we can just return, because if we go right, it's still 1. It's still 2 distance away. And if we go left, it's still 2 away. That being said, how do we want it to work, right, if we have something? Let's just think through the cases. Well, how do we want it to work if we have something? I'll just copy this one and change things around. Right? And I'll remove the beginning and the end just because it tends to mess things up. So what if we change this example, right, to something like this, right, where the nearest 0 is over here, right? I think our output then I need to set up some key bindings real quick just to simplify this process. I'm just gonna type it actually, it's just too slow. And then we'd have 1, 1, 1. Right, what does our go output look like there? Right, well, what's the distance? The shortest distance to 0 is 1, 2, 3, 4, right? 1, 2, 3, 4, so it's gonna be 4, right? And so how do we get that, right? So if we started that first search and we went up, try to go up first, right? Up doesn't exist, so we try to go right. Well, since we tried to go right, we'll try to go up. Up doesn't exist, we'll try to go right. We still haven't found a 0, right? Then we go right, it's not a 0. Try to go up. Up doesn't exist, try to go right. Right doesn't exist, try to go down, right? Down doesn't exist, right? And then, down does exist, so we go down. We try to go up, but up is already visited, right? And so we basically need a way to know when we visited something or not, right? So maybe we could change our approach. What if we just start from a 0, right? Because if we modify the 1 in the array, then when we do a different iteration for a different one, it's kind of hard to know. It's kind of hard to know if we visited it already. So let's change our approach. What if we start with 0 instead? Or I guess we'd have to duplicate it every single time. We have to dupe the map, because if we change 1 to a visited node, like let's just say something like we need to know not to revisit 1, right, when we're iterating through. So I think actually we don't have to. So another way we could do, I don't think we have to duplicate the map actually, but because we have access to the cells, what we could do is add the cell to a set, right? So if we add the cell visited to a set, right, and for each depth first search, this would be a new set, right? So as not to have to keep remaking the map. right? If a cell is already in the set, it means we already visited. So we know that we visited 1 already. So we wouldn't go 1. Right is out of bounds. We'd go down. That would be 0, right? And so we'd return 0 there, right? If we return 0 there, we'd go back up to here, right, where we went down, right? We'd go down, and then from there, so we go up. We can't go up, so we go right. Can't go up, so we go right. Can't go up, so we go right. Can't go up or right, so we go down. We can't go right. So then we'll have 1, 1. So we can't go up, right? So we go right. We can't go up, so we go right. We can't go up, so we can't go right. We can't go up, we can't go right, so we go down, right? Can't go up because it's already visited, right? We can't go right because it's out of bounds. And we can't go down. If we go down, right, we'll get 0. And since we got 0, we'll return 4, right, as the distance. So we'd return 4 as the distance, which would be perfect. Right, but we also want to calculate the other possible paths. Right, so if we return 0, so if we go out of bounds, we could return, you know, something really, really large. So it looks like the way we're going to go with it is iterate through the map, right? Once we iterate through the matrix, if we find a 1, right, we're going to want to start a depth first search and use a set to see if we can only visit places, only visit cells once and calculate all possible paths to a 0, right? Once we reach a 0, return it, and then we'll take the math.min of trying to go in all these separate directions. So I think that makes sense. And so let's try and implement that, right? First thing we need to do is basically find the 1s, and the way we find the 1 is to just iterate through the matrix. So we'll use row and column to make it easier to understand, just to try and pick good variable names and make it make sense. Then we'll have call equals 0. Call would be less than mat sub row dot length, and then we want to do call plus plus, right? So we're going to be able to iterate through the matrix, iterate through the matrix this way, and then we want to say, hey, if mat sub row sub call equals 1, right? Then we want to do that DFS we mentioned. Not, yeah. But if mat sub row sub call equals 1, then we'll start a depth first search, and then from here, right, we'll do mat sub row sub call equals nearest 0 passing mat row call, right, and a new set. Actually, no, we actually need a new set here. Let me see. And then, can nearest 0 be our recursive call? I'm not exactly convinced, so we'll do nearest 0. So we'll actually do it like this, and nearest 0 will actually take the min of 4 different methods. So it's going to take the matrix, right? And then we're going to have R, which is a number, call, which is a number, right? And return number. And so the way to do that, right, like we said, we want to check up, down, left, right. So we have check up, down, left, right. So we have 6 minutes left, so let's speed up. We have check up, down, left, right. And so that's what we want to do. And then we, first things first, right? When do we know that we want to continue, right? So we could actually have a value set to 1 or a non-zero value, basically. So if it's non-zero, what would we like to do? If it's non-zero, it would indicate that we can't use it, right? But if mat sub row, right, sub column actually is 0, right, then we can probably return. And so I'm seeing that, oh no, right, this isn't our, all right, so if we're checking the nearest 0, we're passing in 1 here. We want to check if we can do a depth first search, right? So if the value equals 0, basically what do we want nearest 0 to do? I just want it to be a starting point or a launching pad for the depth first search. So that being the case, we know it's going to return a number, right? This is going to be the nearest 0. It's going to be distance, right? But distance is going to be the math.min, right, of all these other depth first searches, basically, right? And so to start, if the column itself equals 0, right, then we're just going to return 0 because the nearest distance is it, well, this only gets called on 1, so we actually don't even need that value. So let's just do what we were going to do. We need this to be a launching pad for the depth first search. So we'll just say const up equals DFS mat RC, right, and a new set as well as a value which is going to be automatically initialized with the default value for the function. So the way we'll take a input into this depth first search is by passing in the matrix. We'll pass in the row and the column, right, as well as the set, which is going to be a set of strings, right, for constant lookup time, and we'll name it set, right, and we're going to say count, right, which would be, or which we'll say distance, right, which is going to be a number that starts at 0, right. So now we have a starting point, right? So we want to calculate, and actually for the min, we'll also take mat actually no, I think our version of this will handle that. We also want to include the node's value itself, because if, oh no, it's only going to be called for ones. I keep forgetting, it's only going to be called for ones. So now we're in up, right? So basically for every node, actually I think I'm getting actually bogged out with my solution from yesterday, but I think it had potential. So I think what we actually want to do is do that DFS, but starting at different nodes, basically. So when I say up, down, left, right, this is more of where they start. So we say up, it'll be R plus R minus 1, right, to go up, right? So if we go up from this 1, right, does this value equal 0, right? Well, if it equals 0, right, so if mat sub R, right, sub C equals 0, then we'd like to return CT plus equal, have to return CT plus 1, right? Or not even CT, we'll just say distance plus 1. So this would actually give us 1 for this value up here, right? And since we have a 0, we would just return it. It has to be the closest one since it's the first one we run into. Right? So we'd return 1, right? But we also want to run it for right. Right? So what does that look like? Well, the right of it would stay in exactly where we are, but do column plus 1. So now we're in the column next to us. If it equals 0, right, we would return it, which it does. We would return distance plus 1, which would be 1. Right? So let's, for the case of Spartan makes sense, let's run it for this one. If we run it for this one, right, we would go up, right, and we'd see that it does not equal 0, right? So what we do there, we'd return the DFS we return the DFS right. Okay, now I'm understanding. We'd return the DFS. So now, okay, we ran out of time, but I think I'm understanding. I don't know, we don't actually need this nearest 0 function is actually throwing me off. All we need to do, I think, what if we call depth first search here? We call depth first search here, we'll start at this 1, right? And for this 1, we'll call it in these 4 directions, which will also go up, down, left, right, right? And so if that's the case, right, this launching pad here is kind of confusing me, I think. So we'll just call DFS here, right? And if the node itself equals 0, right, then we'll return 1, right? It doesn't, right? So we call it with this 1 here. Does the node itself equal 0? It doesn't, right? So what we want to do, we would go, right? If we go up, right? What if we go up, right? So if we go up, we would find another 0, right? We would return that value, and then basically right? Okay, so I think this could work, and then we'll stitch it all together. So here we'll check if mat sub basically all I want to do is check if it's in bounds. And basically keep going, right? If it's in bounds, right, then do the depth first search. So we'd have to do, so we don't want to return DFS. I think what we want to return is, in this case, distance at the end. There's something confusing me about this problem. If mat, which is a question mark, so we would be going like this. So let's just, so we call it for 1, right? DFS, we're in here. Does it equal 0? It does not, right? And so we want to go, pretty much keep doing this, but for going every direction around us. Going every direction around us, we would call 4 more calls of DFS. More calls of DFS. If we do 4 more calls of DFS, they would also continuously search in all directions as well, and then return their value. So let's just try and follow one run through. We'd go up. All right, so let's just say, so do we want to, so what do we want to check for? Do we want to check that the value exists that we can go up? We just want to know if the next value is in bounds. So we could just check for that up here. We'll say if R is less than 0, right, or C is less than 0, right, or R is greater than or equal to mat.length, right, or C is greater than or equal to mat sub R dot length, right? We want to return infinity. And the reason we're returning infinity is because this is not a valid way to get to a 0. We're out of bounds, basically, right? And so we don't want to return this number. Ideally, there would be another number, right, that we could set it to. So then let's see so let's say if we go left, we'd go out of bounds, we return infinity, right? And let's say there's at least 1 0 in mat, so this is at least 1 0. We don't actually have to worry about returning infinity because we know we'll find at least 1 0, and we'll take the smallest distance there. So here we know that we're in bounds for our current. Or we don't know if we're inbound for our future. So you could say if mat sub R sub C, up, we go up, right, left, down. Up, right, left, down. Oh, I'm getting confused. If mat, what am I trying to accomplish here? Maybe it's because I'm pseudo codeless that I'm running in these circles. Basically, I want to visit four surrounding directions, right? How do we visit the 4 surrounding directions? Right, we have to visit R plus 1, minus 1, and C plus or minus, plus and minus 1. To do that, we'd have 4 calls of this DFS function anyway. So if we're going to call it anyway, what is the prerequisite for in the case that we wouldn't want to run it? Well, I think the case is that we always want to check it, right? Because we want to find the minimum possible path. So maybe what we want to do is do const u equals DFS mat R, right? If we're going to go up, R would be R minus 1, right? C, right? And we're passing in the set, right? And now I'm realizing I'm not exactly certain that we need the set. If we start from here, we'll go up, right? No 0 here, so we go up again, we return a 0. Now we're going to go right from here. It's another 0, we return 2. We go left from here, we return 2. We go down, it's a 1, right? So if we're in bounds, since it's a 1, so we're at this 1 itself again, right? Does it equal 0? No. Is it in bounds? Yes. So we'll call it, so, right, we need a way, basically, to not visit nodes we've already seen, or our starting node, basically. So we basically want a way to not revisit our start. We have the set. right? So we have the set. So I'm thinking, since we're starting at 1, right, we've already visited it, right? So it's not that we don't want to visit it. What if a 0 is here, right? So basically, it's not that we don't want to revisit anything. I think it's the fact that we don't want to go back to our start again. So if we ignore our start, we would have went up, right, up, right, found a 1, found a 0, then right, found a 0, then went down, so basically if a cell starts a DFS, right, this starts a DFS, this starts a DFS, and this starts a DFS, we don't want to call a DFS for a cell that is already starting a DFS. So we go 1, 1, right, out of bounds, we go right, that's away, right, we don't want to go down because we've already been here, right, let's check left, we haven't been there, so we can't go up, we don't want to go right again because we've already been there, we don't want to go down again, we want to go down, then we can't go because we've already been there. We don't want to go right because we've already been there, right? And so I think what we have to do here and this, I guess, is technically sort of a brute force solution now that I'm thinking about it. I feel like I'm half certain we're going to exceed this, because this would happen for 4 versions. But I think what we really want to do is just search the entire map, the entire matrix. So I don't know that we need to go in all directions. I think we just need to search the entire map, search the entire matrix. So if we started at this one, we go because by going up, we end up visiting the whole thing anyway. So basically, we want a mechanism to be able to visit. Let's try this brute force method first. So we'll just do all 4 directions, even though we don't have to. And then basically, we can make a function called codify, or function which just IDs a cell, just take R number, right? C, which is a number, returns a string, and it just returns R C. Basically, you want to put that in the set. So we'd say set dot add so if it starts a DFS, which would be down here, we do set dot add, right, ID RC, right? And so we'd say if set has ID of RC, right, that means we've already visited it. And so we just want to return, maybe we also want to return infinity, right, because this isn't a valid path. So we go up, right, we go up, we can't, so we go right, go up, we can't, so we go right, we go down, we go up again, right? So now we'd be in this thing, we'd say, does the set have this? It does, so we'd return infinity, right? Stop, right? Go right, we can't, go down, right? It's a 1. So we could go into here, then we go left. Right, well, it's already in the set, so we'd return infinity, right? And that would be the last of this run. We go back up here, right? We try to go left. We've already been there, so we return infinity. But since it equals 0, we actually wouldn't get this far. Actually, so if we go up, we'd be 0, right? So we'd automatically just return this 0. So then, if that's the case, we'd stop there, we'd check right, we return 0, we'd check right, we return 0. But for our original example over here, if we start at this 1 up here, we can't go up, so we go right, we can't go, so we go right, we can't go, so we go right, we can't go right, so we go down. Already visited top, and if we return infinity, that's not exactly what we want to do. We'd want to keep going. We just don't want to call a depth first search if we've already seen it. So I don't think this is what we want. I think we actually want this to be part of our checks, basically. So we want to say if set does not have r-1 c, then return DFS r-1 c. But it's not even that we want to return it. We just don't want it to be considered. We don't want it to be considered. We don't want it to be considered. It's like we said, if we do it this way, once we get here, we check up. We've already been up before. So we just don't want to call it depth first search. We still want to call it the other 3. So it's not that we want to return, we just want the value to be set to 3. So I think we could do const up equals if the set doesn't have the value for this, the ID for this row and column, then depth for search. Otherwise, set it to infinity, right? We don't really want to consider this as a possible method. Or maybe we just want to return the cell's original value. So if we don't go up, right, basically we end up with 4 values, right? Right would be infinity, up would be infinity, down would be 1, and left would be 1 as well. The minimum of that is 1. I mean, at left would be like 3. The minimum of that would be 1. But there's always at least one 1 in there, so I don't think we actually have to worry about the infinity. So we'll say D, L, R. Then you go, so if you want to go down, you do +1. If you want to go left, you keep these the same. You go column -1. If you want to go right, go column +1. If you wanted to go left, you would remove both of these, and you do left -1, R +1. And I think what we want to do is return the math.min of U, D, L, and R. And I want to include the node's value itself in there. But I think the node's value itself can be wrong. And so I want it to make sense without running it, because being reliant on running is just not it. So this, let's check if it works for the base example. We call 1 here, right? And our output is supposed to be the same thing, right? If we call it for 1 here, we do DFS, right? Does the cell itself equal 0? No, right? Now does now we're going to check if it's out of bounds. It's not out of bounds. We're going to add our starting cell to the set, right? And then we're going to check up, right? If we go up, is that in the set? It's not. So we do DFS mat R -1. See, we go up. Does it equal 0? Yes, we return 1, right? So we return 1 for that, and we get 1 for all of these as well. We get 1 for all of these as well. We return the min, it would be 1. Let's try a different example, right? Let's try calling it from 1 here, which would return 2, right? So we call it for the cell. Does the cell itself equal 0? No, right? Is it out of bounds? No, so we'd add this as a starting set. We'd go up, right? If we go up, right, does this cell equal, so we push a call of DFS onto the call stack, right? Is this cell, which is 1, 1, does it equal 0? No. Is it out of bounds? No, so we go up again, push another call. So we have 3 calls on the stack. All right, does it equal 0? Yes. Right, so we would return distance +1. We actually haven't been keeping track of distance. So it looks like what we want to do is do 1. We're not even using distance in these calls. We want to do distance plus equals 1. So if we restart, right, we start at 1, right, it's not in the cell, it's not in the set, it's not out of bounds. We add it to the set, right, then we go up with distance +1. So now we're here with distance at 1, right? Does it equal 0? No. Is it out of bounds? No. We add this cell to our set, right? Go up with distance +1. Now we're at 2. Does it equal 0? It does. So we would actually return 3 if we did distance +1. So return distance there. And then that works out, right? But now we're back here, so we'd have to go right. So if we go right, does it equal 0? Yes, we'd still return 2 here, right? And we would now check down, right? Down would be in the cell set, right? And so since that's the case, we would not want to have that added to we'd not want to. So we'd go down, it would be in the cell set, so we would not go down. Then we'd go left, which would also be 2. So since left is in the cell set, we'd actually set it to infinity. And so in this node right here, we would have 2, 2, 2, right? And infinity, we choose the smallest, and it would be 2. We'd return that, right, and go down to here, from which we'll go right, right? It's not in the cell set, it's not out of bounds, right? So we go up, we'd find another 0, it'd be, right, distance 2, so we'd return that, we'd go right, be out of bounds, down is out of bounds, and left is in our cell set, So we'd return the min of all those, which would be 2, and same here. So I think this makes sense at least a little bit. So let's see. Not find name string. Oh, I misspelled a value. And on line 5, I have duplicate identifier R, which is strange. So we have R and C. Call doesn't even exist, it's only C. But I'm not exactly certain how I have a duplicate identifier. We passed in this new set to start. Oh, the duplicate identifier is here at the bottom with RI, so we would do that. And it's saying line 16, expected 1 argument, and I'm using R and C. We're supposed to be using the ID function. And honestly, it might have just been easier to not even use an ID function, but I think for maintainability. This is argument number is not assignable to parameter type set string. Must return a value. Line 23. I want to return mat once we're done. Argument of type number is not assignable to parameter of type set string. So it thinks we're assigning to the set. On line 16, it's saying argument of type number is not assignable to parameter of type set string. So we're saying if the set does not have the ID of R comma C, ID takes R and C, which is 2 numbers, and returns a string. I'm saying my set stores strings. Type number, not assignable to parameter of type set string. So using the ternary here, well, I set it to call DFS, but we set it to infinity. The type error sometimes I just don't, it's just strange. I'm not understanding why that would happen. We have argument of type number is not assignable to parameter type set string. Let's just say it's a set. Oh, are they? No, that doesn't make sense actually. Argument of type number is not assignable. So something's a number and I'm trying to assign it to the set, but I'm not. I'm saying if the set doesn't have this value, I'd like to call DFS. don't understand this type error. I'm honestly confused. We have function ID, which takes a number and a number, which it does, and then we string interpolate it into a string, or we format it into a string, but it's not complaining about the function itself, it's complaining about the invocation. So if I comment these out, take out the has, and I just say has. Does this work? Am I allowed to do this? Because I'm not understanding what I'm not allowed to do. Argument of type number is not assignable to parameter of type string. So, oh, I see. It's in DFS. No, it's not. It's mat, R, and C. Right. Ah, I understand now. It is the order of the parameters, basically. I forgot to pass the set back into the function. So we get the right answer the first time. My guess is we get time limit exceeded. So our output looks a lot like their output, to be honest. Except we have a case where one number is differing. So I would ask, why is that number differing? So we got 2, and so if I can just construct this, right here real quick and break this down. So we got 2 right here, where originally you start with the value 1. If you go down, the nearest value is 1. This makes me wonder if we're not going down properly. Going down, yes, we're not going down properly because we're doing -1. So I think that case should pass. So it gets worse. So here our first row is on the same page as their first, but as things change, so I got 4 here, but I think so we got 4 here, and I think we have 1 and 1. We have 1 and 4, and they have 2. So if we look at the nearby, if you look at the nearby and my nearby, we're certainly off. If you look at this, the nearby, they're saying the nearby 0 is 2 slots away. 1, 2, which it is. But somehow I get 4. somehow I'm getting 4. So if I go left, which is 1, I'm at 4. I got 4. So if I go left, it should be 1, 2. So I think one of my depth first searches isn't making any sense, but they all seem to make sense here. So if I'm going left, though, I don't want to revisit anything I've visited before, but technically once I start here at 4, the only thing I'm adding to the set that we visited would be this one right here. So we would go left, right, then we try and go up, then we try and go right, and so on. Let's just say we return 3, 4, that'd be 3, right, up would be 3. I see, and then we'd go down. If we go down, we would not visit this one again. So I'm seeing why it's saying 4. It's because we're not visiting that one again. And if we build this, so I'm seeing just the way of going about it with the 4 doesn't make sense. I tried to visualize it that way, but I think now it just makes more sense to do it with 1. I mean, you can do it with 1 because you're basically visiting the whole thing through the first call anyway. So if that's the case, in this new version, you would go up, right, then call it again. You'd basically visit the whole thing. I think the visited thing doesn't work as well here because the values can change so much. And so I think we already spent an hour on this problem, so I think we just need to read the solution again, maybe into it a new version. So initially, I think I also should have just tried to implement the brute force version first. I also shouldn't have done that. So our last submissions code. Do exactly what the question asks us to do. For each cell, find the distance of the closest 0. So initialize dis sub I sub j equals int mass for all the cells. Since it's the max, iterate over the matrix. If cell is 0, for all ij cells. Well, a cell can't be 0 if all the cells are now int max. If cell is 0, dis sub I sub j equals 0. Otherwise, for each one cell, iterate over the entire matrix. For each one cell, iterate over the entire matrix. The cell is 0, calculate its distance from the current cell as abs of k minus 1 plus abs of l minus j. The distance is smaller than the current distance updated. So they get the rows equals 0, they return the matrix. Calls equals matrix sub 0 dot size. Then they create a new distance, which is going to be the distance matrix that they return. And they set all the distance matrices to all the elements in the distance matrix to max. I see. So they separate their input from their output. That makes sense. Then they iterate over all the rows and columns, and if it equals 0, then they set that equal to 0 in the distance matrix. Otherwise, we iterate over all the rows or columns in the distance matrix, in the actual matrix, and just keep a running value of the minimum distance so far. What are they using this distance 01 for? I think this is a mess up because I think they meant to use dist01 here because they don't even reuse this variable. But they pretty much use the distance index itself as the minimum value so far. Take the minimum of that, and because it's int max, you always take the smallest one. And that's RC squared, basically. Matrix for each one in the matrix. So now I actually finally do understand this brute force method. I'm going to challenge myself to do the brute force method later today, honestly. No extra space is required other than the space used to store the output dist, and the output does not count towards the space complexity. Now, breadth first search, which is what I was going for here, a better brute force. Looking over the entire matrix appears wasteful, and hence we can use breadth first search. Oh, man. Interesting. I was using, okay, use breadth first search. But I think it's also possible with depth first search to limit the search to the nearest 0 found for each one. As soon as a 0 appears during the BFS, we know that the 0 is the closest, and hence we move to the next one. So if we visualize the matrix as a graph and do a level order iteration, which would be BFS, how do we know that just because we found a 0 here that it's the shortest distance? Zero. As soon as 0 appears during BFS, you know that the 0 is the closest, and hence we move to the next one. Think again, but in this approach, we will only be able to update the distance of 1, 1 using 1 BFS, which could in fact result in slightly higher complexity than the brute force approach. Right, that's kind of what I was doing, except for depth first search, you need to call at least one depth first search for each cell. But hey, this can be optimized if we start the breadth first search from zeros and thereby updating the distance of all the ones in the path. Okay, for our BFS routine, we keep a queue to maintain the queue of cells to be examined next. Start by adding all the cells with zeros to queue. Initially, distance for each 0 cell is 0. Distance for each 0 cell is 0. And distance for each one is int max, which makes sense, which is updating during the BFS. Pop the cell from the queue, examine its neighbors. If the new calculated distance for neighbor I sub j is smaller, we add I sub j to queue and update dist I sub j. So it looks like this brunt of code right here, right? The matrix, right? If the number of rows in the matrix is 0, then we return matrix. Number of columns for that also equals size. So then they create a new matrix where all the values are set to int max. They set all the ones that were already set to 0 to 0, and they also want to process all the zeros. Now that we have all the zeros, right, to process, right, so let's take this example here. We'll turn them all to zeros. right? This is actually a hard example. All the zeros, right? So the queue isn't empty, right? And the first one we have to process is 0, 0. So we pull that off the front of the queue, right? And we're also doing queue.pop. They're also taking it off the front as well. Then for that cell, which is 0, 0, we're going to do 4 iterations. We're going to check 1, 1, 1, 1. We're going to check, right, if it's within bounds, which it is, right, new R and new C, so they're checking if the new angle, right, and the one we're checking is behind us is actually out of bounds, or it's actually above us is out of bounds. So we ignore it. Below us is not out of bounds. So is this new R, new C, which would be int max, greater than 0? Well, yeah, int max is greater than greater. All the ones got sent to int max actually, so it would be 0. Is 0 greater? Yeah, all the ones got set to int max. So we're checking below us. I mean, is 0 greater than 0? No, so we go right. I mean, now we're going what? Behind us, right? Out of bounds. Now we're going to go in front of us, but we're going to return 0. We're not going to do anything. Let's look at what we're going to do. We're going to set it to, well, we're not going to do anything, it seems. Well, okay, so it's this, the new distance, which is 0, greater than the original distance plus 1. No. So let's go to this 0 right here. So we're going to say up, out of bounds, down, right? So we go down, checking if we're in bounds. If dist new R, the new row and new column, is 1 greater than 0 plus 1? No. 1 is not greater than 0 plus 1. Is 1 greater than 0 plus 1? No. So let's say we get to a 1. We're not, because we're only processing zeros. I'm not seeing how this solves the problem. I think we need a better example. So now we're at this 0, right? We're checking below us, right? We're going to say, is dist new R, which is 1, greater than distance of cur dot first and cur dot second, be 0 plus 1? No. I don't see how this algorithm works. I'm following it line by line. I'm just not seeing how it works. We're pushing all of the zeros onto a queue. So let's just say we're processing this. If we start up here, I mean, we go down, 0 is 0, which is new distance, right? Because we're going to go down the first time. It's not even in bounds, right? So we're going to check this one and go, we're going to go down now, right? So is 0 greater than 0 plus 1? That doesn't quite make sense. I actually don't understand how this works. I do not understand how this works. It looks like this algorithm isn't doing anything. Oh, I think I see it. So, lost a little bit of time there. I'm just gonna add, I think it's only like 20 minutes or so. So we have 20 minutes. Oh, yeah, I'm not seeing how the code that they're writing is working. I don't understand it. So let's try and read this. The key is to put all zeros in the queue from the start. That way, in case of multiple zeros, they will converge their results on each other at the same time, i.e. from the 0, walk one layer out at a time and mark the result one layer away from 0. Only go as long as there's no answer given, answer from another converging 0, 0 elsewhere in the grid. So default is -1, we have a queue. Their result is a matrix in there which they're trying to duplicate, and the default value is going to be -1. For R and range length of mat, so here they're saying if the original matrix was set to 0, then we're going to append, they're going to add this row column pair to the queue, right? And the queue also seems to be getting a third value, which the depth, I guess they're saying, is 0. 0 steps to get to this 0. And then result R sub C equals 0. So visited, so R sub C equals 0. Then we have visited equals set. So they are using a set. So while queue row call depth queue.pop, so while the queue exists, we're gonna have a row, a column, and a depth. Right? If row and the column in visited continue. Right? And we did something similar, except we used depth first search. But I think we end up in I think I see what I'm understanding. In depth first search, you can prune your infinite calls because you can't visit a spot twice. But if you visit the spot, because you can go around positions, a spot you mark as already visited, you'll still need to revisit. But I thought I solved for that with, but you actually can't. I think I see what they're getting at. If in bounds not visited and no result from another 0 yet, visited.add row. So the queue has all the zeros in it, and the results matrix also has zeros mapped as well. So the only thing that we can see, the difference between the mat that they pass in and the result, is that the matrix now has zeros where the zeros are and -1s where the 1s are. Now we have a set, so we're going to pull the row, column, and depth, which all start at 0 for all zeros. and we're going to say visited.add row and column. So we don't want to revisit this. If results of row sum column equals default, no other 0 has gotten here first. So result row sub col equals depth. So if this equals -1, right, then we want to set it equal to the depth. If in bounds, not visited, and no result from another 0 yet, then we add it to the queue to be processed. So full visual example, we have a grid 0, 1, 1. The result is going to keep the zeros internal, the ones negative. Whoa. Oh yeah, result equals -1, -1, -1. First, all zeros go on the queue for BFS. No, wait, result mat sub r sub c equals 0. And yeah, they append the queue to keep track of all the zeros and the depth, which is going to default to 0. And we said r sub c equal to 0. Which means all the ones should still be -1. So it should look like this. First, all zeros go on the queue for BFS, and we mark the result since we know 0 is 0 away from 0. At each step of breadth first search, children are added if in bounds, not visited, and has default -1 in result. To visit, the depth that's been passed on is added to result. The 0 spot would pass 0 plus 1 to its children. So children and so on. Children visited from 0, 0. Children visited from 2, 2. To visit, the depth that's been passed on is added to result. The 0 spot would pass 0 plus 1 to its children, and so on. So we're kind of, there's some way we're retaining this 0 value's depth or passing it on to the children. And then when we get from 2, 2, well, 2, 2, set this to 1, this to 1. Children visited from 0, 1, 0, 0, 1. Children visited from 1, 0. Some children visited from 1, 0. So if a row where we're only pushing zeros onto the queue, though, that's what I don't get. We're only pushing zeros onto the queue, so how are we even visiting these ones that equal default? So for the row in the column, we check all the squares around it. I see, and then we end up adding that to the queue. I see. Geez, yeah, we just need more BFS practice. We need more BFS practice. So this one is O1 matrix. This is a graph problem. This is the first graph problem. No, floodfill was a graph problem. We order by topics. Clone graph course schedule. So O1 matrix is just a different problem. O1 matrix is just a different problem. I feel like though, yeah, I really feel like I'm missing out on not having a set of different iterations that I can pull out of my pocket. So I feel like this problem we'll have to do again and see if we can intuit the solution again. So we'll try it again tomorrow or later today. But for the last 10 minutes, I'll probably just have to do longest palindrome, or we'll look at similar questions. Yeah, give me. So we have longest palindrome, which I tried yesterday. Couldn't really figure it out. I read the solution, and I think I'm sort of kind of getting the intuition. So given a string S, which consists of lowercase or uppercase letters, return the length of the longest palindrome that can be built with those letters. So the first time I tried this, I thought maybe I could generate all possible permutations of a string and simply check structurally for that string if it could be a palindrome, because you can check if something could be reconstructed to make a palindrome in terms of rearranging. Basically, there was an algorithm you could use that you could check if you rearrange the is an algorithm you can use to check if a permutation of the string could be a palindrome. So if that's the case, then we could generate all possible strings. But now I'm seeing that certain length of the longest palindrome with those letters. It's also possible, using the hints from that algorithm itself, that if we build a map of letters to occurrences, we have A equals 1, B equals 1, C equals 4, and D equals 4, D equals 2. The output here is the longest palindrome we can make is 7, right? Because only A or B can be our unique value. That's the case, I think initially it seemed like we could iterate through and then just do mod 2, right? And if we already have an odd number, right, we could say that we have our odd value already, and then ignore the other values, not ignore the other odd occurrence keys. From there, we could just basically do mod 2, right, and plus the number of characters to a length, which would give us the length of the string. Now, why doesn't this work? And I think it doesn't work because it's possible that a number, we're doing mod 2, which is checking if we have an even number of numbers, even number of values. But if we have 5, then we get an incorrect value here. And I think what that means is we actually want to subtract 2. We want to subtract 2, right? If we add a pair, right, we could subtract 2 and then end up, going forward again and then subtracting 2. So we have to keep iterating over the map, right? But that being the case, it would be faster to just be able to add, if we can divide by 2, right, and floor the answer, then we'll pretty much be able to know whether or not we pretty much know that we can add basically, you know, the 4 characters or the 2 from this that we want to add, right? So, or actually 4, right? Because 5 divided by 2 would be 4. So you actually want to add 4 characters, right? You want to add 4 characters, right? And then not use that last value, right? So maybe we could do it in a 2 pass. If we see the map, right? If we use the map, we could do divide by 2, and we could just keep adding those characters as we move forward, right? Once we equal 0, then we're good. Once we have 0, we're good. Or we reach 1, then we know I have used an odd version. So let's try a version of that. So I think our goal is to load S into map, right? And then from here, we'll iterate over occurrences, right? And then inside we'll say while occurrences is greater than or equal is greater than 1. Right? And this would be a 2 pass. Iterate over occurrences, because here we want to get all the pairs. First pass pairs, second pass odds. Iterate over occurrences. While occurrences is greater than 1, right? What do we want to do, right? Well, we'll have the length of the string. We want to divide it by 2 and pretty much seal the answer. So if we do length over 2, right, we do pretty much len plus equal length over 2, right? But here we would floor it, right? But in terms of the occurrences, right, we'd update, we'd say oc equals the math.seal of length over 2. Why? Because if we have 3, right, and we divide it by 2, we would get 1.5, right? Actually, we want to floor this as well. So if we do 3 divided by 2, right, it only goes into it once, right? So occurrences would now equal, it's like you don't even want to divide. I want to say 3 mod 2. No, well, mod 2 is too hardcore. We want to know how many times it goes into it. Say 3 divided by 2, we know it goes into it once, which is good. Right, since it goes into it once, we'll have a value, right? So how many times it goes into it.